In this video, we will talk about coordinate systems induced by a basis. This is our overview sheet, which will take a few moments to go through, and then we'll back up and go through each topic in more detail with more examples. We will start with this comment that if a basis B for a vector space V contains n vectors, then B imposes a coordinate system that will make V look like Rn. And so this here is important because what it says is, all vector spaces, they want to look like Rn. So Rn is not just our canonical vector space. In fact, all vector spaces deep down have the same structure as Rn. And we know part of this because they all share the same algebraic structure as far as vector addition and scalar multiplication go. But we'll also see in this video, for n vectors, it'll be isomorphic to Rn. The first theorem we will have is the unique representation theorem that says if B is a set of vectors, n vectors, and it's a basis for V, the vector space V, then for each vector x in V, there exists a unique set of scalars, C1, C2, up to Cn, such that x can be written as a linear combination of the basis vector, that is C1b1 plus C2b2 up to Cnbn. And the definition then of coordinates, if B is a basis with bases vectors b1, b2 up to bn, then the coordinates of x, of a vector x, relative to the bases are the weights, c1, c2 up to cn. So once we write x as a linear combination of our bases vectors, these constant coefficients then will be our coordinates. And we denote that by saying x, the coordinates of x with respect to b, here we put the name of the basis, and I kind of make this b here for the script b, is equal to the coordinates. So you can see how it's starting to look like Rn already. We can graphically represent these coordinates. When we graph normally, like say for example the number 1, 6, we are using the standard basis 1, 0, 0, 1, and we do this without even thinking about it. But you can picture this as being this coordinate 1 times the first standard basis vector 1, 0, and then plus the second coordinate 6 times the second standard coordinate basis 0, 1. And then here you have 1, 6 plus 0, 6, those two vectors, you use your parallelogram law, and that will plot the point on the graph here of the point 1, 6. Similarly, you can now think of this new basis as having a new set of coordinates. So you still have your 1, 0, and then now for our second basis vector, we have 1, 2, which is this little line here. So these are the two axes of our new coordinate system. So when we plot 1, 6, which is equal to negative 2, 3 with this new basis, then we multiply our negative 2 times our first basis vector, and then our second coordinate times our second basis vector. And you can see when you add these together using the parallelogram law, you will still get the same point in space as when you used the standard bases. We will see that the matrix consisting of the standard bases will change coordinates from basis B to the standard basis, and then the inverse of this matrix will transform a vector x in the standard basis to a vector in the basis B. And then we have this theorem here, the coordinate mapping. So if we have a basis and it's a vector space for V, then the coordinate mapping, this matrix here from x to the coordinates xb, is a one-to-one linear transformation from V to Rn. So in other words, now we have a mapping from our vector space V to the very familiar vector space Rn. So here we have the point choosing a basis for a vector space introduces a new coordinate system in V, but the coordinate mapping connects this possibly unfamiliar space V to the familiar space Rn. So every vector space then is essentially isomorphic because it's one-to-one and onto Rn. So the coordinate mapping is an important example of an isomorphism from V onto Rn. The notation and terminology for the two vector spaces may be different, but the two spaces are indistinguishable. Every vector space calculation in V is accurately reproduced in Rn and vice versa. This is it for our overview, so now we'll back up and look at these ideas in more detail. The unique representation theorem says if we have a set B of vectors b1, b2 up to bn, and there are a basis for a vector space V, then each vector x in V, there exists a set of scalars c1, c2 up to cn such that x, the vector x, can be written as a linear combination of your basis vector c1, b1 plus c2, b2 up to cn, bn. The first part of this proof is quite straightforward since we know that the basis, this is my script B, the basis spans the vector space V, then for any x in V, there exist scalars such that x is a linear combination of B. That's just what it means to span. The second part of our proof is proving uniqueness. And the standard way of proving uniqueness is to assume first that it's not unique. So there's not a unique set of scalars. That, in particular, you're going to assume there's another set of scalars that satisfy this condition. But then through whatever's algebra or other properties, theorems, definitions, you're going to show that the two must be equal. So here again, we're going to assume that in addition to C1, C2, Cn that satisfies this property, x is equal to C1, B1 plus C2, B2 plus Cn, Bn, there exists another set of scalars, D1, D2 up to Dn, such that x is equal to D1, B1 plus D2, B2 up to Dn, Bn. Now we have that both of these x's must equal each other, so we can set this linear combination with the C scalars and the linear combination with the D scalars equal. But now because B1, basically we can go, remember, and also these vectors, B1, B2, Bn, they're linearly independent, and that's important because the only way you're going to get B1 is with the C1 and D1. You're not going to get B1 by combining these other vectors here. So moving this D1, B1 over here, subtracting from both sides of the equation, then you have D1, or I'm sorry, I moved C1 over here. So subtracting C1, B1 from both sides of the equation, I'm going to have D1 minus C1 times B1. Moving this over, I'm going to have D2 minus C2 times B2, all the way to Dn minus Cn times Bn. And that's going to be equal to 0, right? Because I subtracted everything over, so this side's now 0, which must mean that each of these scalars must be equal to 0, which means D1 is equal to C1. Therefore, the representation is unique. Our first example of this idea then of coordinates is, let's say we have a basis where the first basis vector is 1, 0, the second basis vector is 1, 2. Suppose x and R2 has coordinates in this new basis, so the coordinates of x with respect to b1, b2 is equal to -2, 3. We want to find x, and by x here we mean x in the standard basis. So then x, remember this coordinate means this -2 is the coefficient for 1, 0, and the 3 here is the coefficient for the second basis vector, 1, 2. So what we get is 1, 6. And again, written in the standard basis, this would be 1, 1, 0, plus 6, 0, 1. When we don't have a basis indicated here, it's understood that this is the standard basis. And now we come to the graphical interpretation of these coordinate systems. So we have 1, 6, which is equal to -2, 3 with our new bases 1, 0, and 1, 2. We are going to start by graphing 1, 6, and we know how to graph that, right? You go over 1, up 6. But let's think about this in terms of our standard bases, which is 1 times our 1, 0 vector plus 6 times our 0, 1 vector. So 1 times 1, 0, that's just 1, 0. But now we have 6 times 0, 1. So if I take our second standard basis, I need to scale it by 6 now. So this is my scaled standard basis. And now, according to my parallelogram law, Now I have my vector 1, 6. We are going to do the same thing using our new bases vectors 1, 0, which I have in blue. And now our second bases vector is the vector 1, 2. So I have this in blue. This is now going to be our new axes. We're no longer using the 0, 1 and 1, 0 as our bases. These are our axes now, our new bases. I have to now tilt my graph paper. My 1, 0, well, that still gives me this horizontal x-axis, but my 1, 2 now tilts my x-axis. It's a little bit skewed over. And the next thing I need to do is for each of my axes is scale it. So my 1, 0 gets scaled by -2. So it's just the same horizontal, but in the opposite direction, scaled by 2 units. So here I have my -2, 0. Then my 1, 2 vector needs to be scaled by 3, which I did right here. It's kind of nice having this graph paper because, right, you just extend this 2 more units, and this is scaled by 2, and then another 2 units, and it's scaled by 3. So here I have 3, 6, which is 3 times 1, 2. Now I have my 2 vectors here that I need to do my parallelogram law. Moving this vector over here and this vector up here, you can see that they intersect at 1, 6. So physically, the point that I graphed in standard coordinates is the same point that I graphed with this new basis, which is, it's like polar coordinates. It's not like the points move around, but you're expressing them with different coordinates, and that's exactly what we did here. We expressed this same point in terms of our new axes, our new basis. Your book has this example about crystallography, and it says the description of a crystal lattice is aided by choosing a basis U, V, and W for R3 that corresponds to 3 adjacent edges of one unit cell of a crystal. So these are the different types of unit cells. And here we have a basis that's kind of skewed, this basis that's body-centered, this one that's face-centered. An entire lattice is constructed by stacking together many copies of this one cell. There are 14 basic types of unit cells, and 3 are displayed below. And one thing I'm going to say is, in this coordinate system, this dot here is like halfway U, halfway V, and then 1 unit up in W. Now that we know the graphical interpretation of coordinates, and I shrank this down very tiny, we can talk about the coordinate mapping. So we can change coordinates from our bases vector to standard bases, and we would use this matrix, which is simply the matrix using the bases as your columns. And this matrix then will change from the B matrix to the standard bases. And then the inverse will transform X to your B bases. And we'll do an example with these matrix of transformations. So let B equal B1, B2, where B1 is 2, 1, and B2 is -1, 1. Find the coordinate vector X, this X, in terms of B. So of X relative to B. So X is equal to 4, 5 in the standard bases. So what we're asking then is for 4, 5 to be written as a linear combination of 2, 1 and -1, 1. So we have this vector equation here, 2, 1, x1 plus -1, 1, x2 is equal to 4, 5. So now we're going to look at our matrix equation, which is 2, 1, -1, 1, x is equal to 4, 5, and we're solving for x. So I'll look at the augmented matrix, which I row reduced, which is quick to do, fortunately, and what I get is x2 is equal to 2 and x1 is equal to 3. So these are my new coordinates and my new bases, my B1, B2 bases. So x1 is equal to 3 times B1, 2 times 2, 1, and x2 is equal to 2 times B2, which is -1, 1. And if you multiply that out, you will get 4, 5. So 3, 2 now are my coordinates in my new bases. So the note that I have now is our matrix 2, 1, negative 1, 1, and again, these just come from my bases vector. B1 is 2, 1, B2 is negative 1, 1, will transform from the beta bases to the standard bases. The inverse then, the inverse matrix will transform from our standard bases to our new bases B. Somewhere later, we'll have an example of this inverse matrix. We have this theorem that says the coordinate mapping represented by the matrix over here, P of B, is a one-to-one onto linear transformation from V onto Rn. And the significance of this is when you have a one-to-one onto transformation, you have an isomorphism. And what isomorphism means is your two spaces, V and Rn, are essentially the same, that the coordinates, the vectors in V are essentially a renaming of the vectors in Rn. And once you get the mapping of the naming from one vector to the other, from V to Rn, then whenever you do calculations of vector addition, scalar multiplication in V, they're totally going to correspond to the same vector calculations in Rn. We're going to start by proving the one-to-one and onto. The proof of linearity is in your book. First, a quick review of what it is to be one-to-one. If you have a function from some domain to a range, to be one-to-one means that everything in this range has at most one thing mapped to it. Here's an example of something that's one-to-one. We have two items, and for this element, there's only one thing that maps to it. Over here, for this element, there's only one thing that is mapped to it. Here is an example of something that is not one-to-one because we have this element here mapped to it by this element, also by this element. There's a standard way to prove things are one-to-one, and actually I'm going to label this now. So we're thinking of this as a function that maps from space A to space B, for example. And here we have a function, another function f that maps from space A to space B. This function here is one-to-one, this is not. I'm also just going to label this as element A1 and this is element A2. We can just label this as B1 now. So to prove that things are one-to-one, we're going to assume first that it's not one-to-one. So it's sort of a proof by contradiction. We're going to have f of A1 mapped to the same element as f of A2. But then we're going to do some calculations and show that necessarily if f of A1 is equal to f of A2, A1 must equal A2. So this is the approach we're going to take. So I wrote that kind of here. To show that f is one-to-one, we show that if f of x is equal to f of y, then x must equal to y. So if I want to show that this mapping is one-to-one, I need to show that there are two elements. I'm just going to choose x and y as vectors in V that get mapped to the same coordinates with respect to beta. So here I have my coordinate x with respect to beta, and y, well, it does get mapped to y with respect to beta, but I'm going to set these two equal, just like I did here. Then what I want to show is necessarily x must equal y for this statement to be true. I'll start with, since beta is a basis, then x is equal to scalars a1, a2 up to an times the basis vectors, that is a1, b1 plus a2, b2 up to an, bn. Y, similarly, y is in the vector space, so there's a set of scalars c1, c2 up to cn, such that y is equal to c1, b1, c2, b2 up to cn, bn. And what we have is x written as coordinates in terms of beta is equal to then, because here we've written it out, a1, a2 up to an, then y with respect to beta must be equal to c1, c2 up to cn. Now, if our x with respect to b and y with respect to b are equal, then we have a1, a2 up to an. This vector here is equal to c1, c2, this vector here up to cn, which, because of the way vectors work, that must mean that a1 is equal to c1, a2 is equal to c2, all the way down to an is equal to cn. But if they're equal, that means these two vectors, x and y, must be equal. Next, we'll prove onto, which we've been doing because we had to prove things were onto Rn. So we're going to say for all vectors u and Rn, there exists some vector x such that x coordinate with respect to b is equal to u. And for whatever reason, this is hard for me to understand just in symbols, so I drew a picture. I'm saying I have this mapping from Rn, I should probably say Rn, where we have x in terms of our standard bases, and then we map it to a different coordinate system with respect to our new bases b. So what we're saying is if to map onto, that means everything over here, if we choose some coordinate with respect to b, that we'll be able to find some vector u that gets mapped to this coordinate. So we want the vector here in this space that gets mapped to this coordinate. Let's just pretend that our x vector is 1, 2. So this is the coordinate with respect to b. If I want to know what element x gets mapped to 1, 2, b, then it seems like what I would want to do is 1 times b1 plus 2 times b2. And that's actually, it doesn't just seem that's what I want to do, that's exactly what I want to do because this is what gets mapped over here. So let's write that in a general form. So I have our little picture here for reference. So the x we want to construct is that particular linear combination the way we did here. We're going to put u1 times our first bases vector plus u2 times second bases vector up to un bn. Remember, and we can do that. And in fact, b1, b2 up to bn, they span the whole vector space. So this is x is a vector in the vector space. So now we have that x with respect to b is equal to u1, u2 up to un, which is exactly what we wanted. We wanted an x such that x coordinates with respect to b is equal to our random variable Rn. Now let's talk a little bit more about this idea of isomorphism that we get from being one-to-one and onto. I have here a picture of 4 elements in our set B and 4 elements in our set A, and you can see that this picture here is one-to-one as well as onto. It's one-to-one because every element here in B is mapped to by at most one other element from A. It's onto because every element in B, I'm thinking there's 4 elements in B, have something that gets mapped onto it. Here, in contrast, is one-to-one, but it's not onto. It's not onto because there's this element here that doesn't have anything mapped onto it. Here we have something that's not one-to-one, but is onto. It's onto because there are, well, I could put another element here. There are 4 elements. Well, no, I can't. Okay, because there are 3 elements here in B, and then and each of them have something mapped onto it, which is why it's onto, but it's not one-to-one because here you have this one element that's mapped to two different things in A that map to it. And if one single element of A mapped to 2 things, it's not even a function. So this is what a one-to-one and onto transformation looks like. And what it says is essentially that the elements here are essentially the same if it's one-to-one and onto as the elements in set A. It's almost like you just renamed this A1 element, you just renamed it to B1, and you renamed this A2 element to B2, this A3 becomes B3, and this A4 becomes B4. So again, if it's one-to-one and onto, it's almost just like a renaming, and all your additions, so if you add A1 plus A2, let's just say you get A4, that means over here in the B space, if you add B1 to B2, you're going to get B4 because A1 corresponds to B1, A2 corresponds to B2, and A4 corresponds to B4. So these addition properties, scalar multiplication, they're totally analogous in between the 2 spaces because the 2 spaces are simply a renaming of the vectors and the structures all come with it. So the significance of this, it's a big significance, is any vector space has this isomorphic mapping from the coordinates to Rn. So all your vectors, if it's a waveform, if it's audio, light, those are the waveforms. If it's a Rochambeau game, whatever vectors you have, paints, which are also kind of like waveforms, but whatever vector you have can be then translated into a vector into Rn. And I'm just going to mention, because I talk about waveforms a lot, so how do you transform a waveform, like an audio waveform, into Rn? Do you remember in calculus when you had those Fourier series, so you could represent any curve by, well, an infinite series if you wanted to get it exact, but you could approximate it if you didn't have an infinite series of sine waves of different frequencies? The coefficients you put in front of each sine wave will be your Rn, because your sine waves at different frequencies will be your bases. Our next example, let beta be the standard basis of the P3 space of polynomials. That is, let b equal 1, t, t squared, and t cubed. A typical polynomial in P3 has the form a0, that's a0 times 1, a1 times t, a2 times t squared, and a3 times t cubed. Since p is already displayed as a linear combination of the standard basis, we conclude that the coordinates of p with respect to this basis is a0, a1, a2, a3. Thus, the coordinate mapping p to pb is an isomorphism from p3 to r4. All vector space operations in p3 correspond to operations in r4. So to look at this, let's consider we have two polynomials. The first one is 2, 3t squared t cubed, and the second one is 4t plus 2t squared. If we add these two polynomials, we would get 2, and then I have my 4t, I have 5t squared and t cubed. I can convert this to a problem in R4. So P1, its coordinates in the basis, it's 2 is the constant. There's no t term, so that's 0. There's a 3t squared, so here's the 3, and there's a 1t cubed. For P2, there's no constant, so there's a 0. There's a 4t, there's a 2t squared, and no t cubed. So this is the coordinates of P1 with our basis b, and this is the coordinates of P2 with respect to our basis b. Now when we add these two together, we get 2, 4, 5, 1, which is exactly the same polynomial. This would be 2 for the constant, 4 times t, 5 times t squared, and t cubed, which is exactly the same thing we got when we added the two polynomials together. So again, we can essentially, this vector space of P3 is exactly the same vector space as R4. We just rename these polynomials with these coordinates in R4. And then exactly what we do when we do scalar multiplication or addition corresponds to the same exact calculation in R4. Our next example is use coordinate vectors to verify the polynomials 1 plus 2t squared, 4 plus t plus 5t squared, and 3 plus 2t are linearly dependent in P2. I am going to start by converting these three polynomials into coordinates into that last basis from our last, like the canonical basis for polynomials, which is 1t, t squared, and there's no t cubed here, so we can stop. So P1, which is equal to 1 plus 2t squared, we have a 1 for our constant, 0 times t, and then 2 times t squared. P2, we have 4 plus t plus 5t squared, so 4 is our constant, 1 in front of the t and 5 in front of t squared. And P3, which is 3 plus 2t, is 3 for our constant, 2 in front of the t, and 0 in front of the t squared. To find if these three vectors now are linearly dependent, which will imply that the polynomials are dependent, we take these vectors as column vectors in our matrix and set them equal to 0. So we're looking at the equation AX equals 0. And if we can find a non-trivial solution, then they will be dependent. If there's only the trivial solution, they're independent. So here we row reduce the matrix. We get x3 is free, so that means there's a solution. x2 is equal to minus 2x3, and x1 is equal to 5x3. In other words, if we let x equal to 1, then x2 will equal to minus 2, and x1 will equal to 5. So I'm going to put 5 in front of my first vector, which is 1, 0, 2, a minus 2 in front of my second vector, which is the 4, 1, 5, and a 1 in front of my third vector, which is 3, 2, 0, and set that equal to 0. And you can do the math, right? This would be 5 minus, 8 plus 3, that would give me 0. And you can do the rest, and you can see that this linear combination will give us 0. So I'm going to write then one of my vectors, my 3, 2, 0, and I chose this one because it has a 1, so I don't have to divide anything. So my 3, 2, 0 is equal to, moving this 2 to the other side of the equation, I get 2 times 4, 1, 5. And then moving this to the other side of the equation, I get minus 5, 1, 0, 2. So I have shown that 3, 2, 0 is dependent on the other two vectors. And now I can convert this back to my polynomials. So my 3, 2t plus 0t squared is equal to 2 times my 4 plus t plus 5t squared minus 5 times 1 plus 0t plus 2t squared. So now I have written this third polynomial as a linear combination of the other two. And I figured what I used though to figure this out, I could have used algebra here, but what I did is I did a transformation to this question into vectors, and then I used my techniques from linear algebra to solve for the linear combination. This next question is let beta be a basis for H, which is equal to the span of V1, V2, where V1 is equal to 3, 6, 2, and V2 is equal to negative 1, 0, 1. Determine if X, which is equal to 3, 12, 7, is in H, in other words, is X in the span of V1, V2, and if it is, find the coordinates of X relative to the bases. If X is in the span of V1 and V2, then X, 3, 12, 17, can be written as a linear combination of V1, which is 3, 6, 2, and V2, which is negative 1, 0, 1. So to solve this, I'm going to use the matrix equation, these two vectors forming AX equals this vector here. So the augmented matrix now is my V1, V2, and then my X vector. I row reduce it, and I find that X1 must equal 2 and X2 equals 3. In other words, X, which is equal to 3, 12, 7, is equal to, X1 is 2 times my first vector, 3, 6, 2, and 3 times my second vector, negative 1, 0, 1. So this is how X is written as a linear combination. Then to find the coordinates of X relative to B, that would be then these coefficients here, 2 and 3, the coefficients in front of the bases. So 2, 3 with respect to this basis B. Now we have gone over all the topics in this video. So I do have another, I think, 3 problems, maybe just 2. I think it's just 2 problems. But since we've gone over all the material, I'm going to suggest after each problem statement that you pause the video and give the problems a try before you look at the solutions. So I know I said there were 2 problems, but this first problem comes with part A, B, and C. So let B1 equal 1, 0, 0, B2 equal negative 3, 4, 0, B3 equal 3, negative 6, 3. And then we have the vector X, which will equal to negative 8, 2, 3. And the problem is to show that B, which is equal to B1, B2, B3, is a basis for R3. The second part is to find the change of coordinates matrix from B to the standard basis, and last, find the coordinates of the vector X in terms of our basis. I'm going to start by showing that B1, B2, B3 is a basis for R3. And the 2 things I need to show are 1 is that the vectors are linearly independent, and 2 that they span the space, they span R3. So first, they are linearly independent. So I write B as our matrix, 1, 0, 0, negative 3, 4, 0, 3, negative 6, 3, and then I set them equal to 0 to see what the homogeneous equation looks like. Fortunately, this is already an echelon, reduced echelon form for me, and I'll see that x1, x2, and x3 all need to equal to 0. So b1, b2, b3 is linearly independent. Next, I need to show that b1, b2, b3 span R3, and I can do that using the invertible matrix theorem because I have this here. There must be something in the invertible matrix theorem that says being linearly independent means they span R3. But just to be this way, I'm also going to show it, I don't know what to say, the old-fashioned way. So let's let U be our representative vector in R3. So U has components or coordinates U1, U2, U3. Show that U now can be written as a linear combination of B1, B2, and B3. So in other words, we're going to show that Bx equals U has solution. So I have my matrix here that is composed of my basis vectors, 1, 0, 0, that's B1, negative 3, 4, 0, that's B2, and 3, negative 6, 3, that's B3, my third basis vector, and I'm going to set it equal to my vector U with components U1, U2, U3. And again, this wasn't too bad because this is already an echelon form, so I get that x3, my first coordinate is equal to U3 divided by 3, my x2 is going to be 1/4 U2 plus 6, x3, and x1 is u1 plus 3x2 minus 3x3. So the idea is you can find, once I give you a u, like with numbers, like if this was 2, 4, 6, you would be able to solve for x1, x2, x3, such that x1, b1 plus x2, b2 plus x3, b3 would equal to u. So bx equals u has solution, and therefore the set b1, b2, b3 spans R3. And therefore, since this set is both linearly independent and also spans R3, B is a basis. Our set B is a basis. Part B of this problem is to find the change of coordinate matrix from B to the standard basis. So what we do have here is, if we take b1, b2, b3 as column vectors of a matrix, so I have 1, 0, 0, negative 3, 4, 0, and 3, negative 6, 3, that'll convert from our coordinates with respect to b into our standard basis. Oh, and that's exactly what they wanted, from b to the standard basis, so we're done. It's this next part that's going to take a little more work. We want to find the coordinates of x with respect to b. So here we have the coordinates of x with respect to the standard basis. We have this change of coordinate matrix, yeah. Except that this takes x with respect to b and gives us the standard vector. We have the standard vector, we need to find this x with respect to b. So in other words, we need this inverse matrix here. Which actually, it's good, we haven't done this in a long time, so this will remind you how to find the inverse matrix. You take your matrix, you put it alongside the identity matrix, and then you do row operations until this first half becomes the identity matrix. All the while, you're doing it to the entire row, so it will transform your identity matrix then into the inverse matrix. So here, in other words, the second half, what used to be the identity matrix, gets transformed into the inverse matrix. This is the matrix that will take the standard, the coordinates from the standard basis and convert it to coordinates with respect to the basis b. So the this change of coordinate matrix is 1, 0, 0, 3/4, 1/4, 0, 1/2, 1/2, 1/3. Maybe I'll make it a little bigger. This is our change of coordinate matrix to go from x for the standard coordinates to x with respect to b. So now I can multiply my x in standard coordinates, which is negative 8, 2, 3, times my matrix. And actually, matrix multiplication is not commutative, so I should have said I multiply my matrix times my vector. And when I do the multiplication, what I get is negative 5, 2, 1. So in other words, my 8, 2, 3, my negative 8, 2, 3 vector is equal to the negative 5, 2, 1 with respect to this basis here. And I can verify that by taking my negative 5, 2, 1 and multiplying by my basis vector. And what I should get is x. So I have my negative 5 times b1, which is 1, 0, 0, my 2 times b2, which is negative 3, 4, 0, and my 1 times b3, which is 3, negative 6, 3. And if you multiply them out and add together, you will indeed get your x, negative 8, 2, 3. This next problem is you're given a basis 1 plus t, 1 plus t squared, t plus t squared. It's a basis for P2. In other words, polynomials of degree 2 or less. Find the coordinates of this polynomial, 6 plus 3t minus t squared, relative to this basis here. So it's not the standard basis for polynomials, because that problem would be really easy. The coordinate would be 6, 3, negative 1. But it's this new basis for P2. So I've written my polynomial 6 plus 3t minus t squared plus 0t cubed. Why did I do this? I'm not sure why there's a t cubed. I didn't need that because we're in P2. Well, certainly 0 is appropriate, but anyway, so I'll just get rid of that. And I want to find that as a linear combination, so my x1 is my first constant times my first basis vector, 1 plus t, plus x2 times my second basis vector, 1 plus t squared, times x3, my constant, times my third basis vector, t plus t cubed. And multiplying this out, I get x1 plus x1t plus x2 plus x2t squared plus x3 times t plus x3 times t squared. I have to admit, since we've been talking about coordinates, my attempt was, I was thinking about putting this in terms of R3, but let's do a little bit of algebra first. What we have, if we look at our constant terms, so our constant term should equal to 6. So 6 should equal to x1 plus x2. So these are our two constant terms, and that'll be equal to our 6. And then next, we need our terms that are multiplied by t. So on this side of the equation, I have 3, and then things that are multiplied by t, I have my x1 times t, and I have my x3 times t. So that's on the, my 3 must equal to x1 plus x3. And then last I have my t squared terms. So that's minus 1 on this side, and over here I have an x2 and an x3. So these are the three equations that I need to satisfy. So if you look at this, I have 3 equations and 3 unknowns. I know how to solve that. I can take my augmented matrix, so my 6, 3, negative 1 goes on the far right-hand side. My matrix here, I have my x1 and x2 are both coefficients 1, and my x3 is 0 for my first row. My second equation, I have x1 is equal to 1, x2 is equal to 0, x3 coefficient is 1. And then here on the last row, I have 0 for my x1 coefficient, and then my x2 and x3 have 1 as coefficients. So now I can row reduce this, and what I get is that x3 is equal to negative 2, x2 is equal to 1, and x1 is equal to 5. I can put these coefficients now in front of my bases. So I have 5 times my first basis vector, 1 plus t, my 1 times my second basis vector, 1 plus t squared, and then my x3 is minus 2 times my third basis vector, t plus t cubed. And when I multiply this out, you can see I did actually get this polynomial over here, exactly what I was trying to find. So going back to the question though, I want the coordinates for this vector, p, for this polynomial, and that's simply the coefficients, 5, 1, negative 2. So this polynomial has coordinates 5, 1, negative 2 with respect to our basis beta here. So reviewing what we have discussed in this video, first we said that if we have a basis for a vector space containing n vectors, then B imposes a coordinate system, and that coordinate system is actually isomorphic to Rn. What we had was, we started with the theorem of unique representation. We had B was a basis consisting of the vectors b1, b2 up to bn for a vector space V. Then for each x in the vector space, for each vector x in the vector space, there exists a unique set of scalars, c1, c2, cn, such that x can be written as a linear combination of our basis vector. In other words, our vector x is equal to c1b1 plus c2b2 up to cn bn. So then we can define coordinates. So suppose we have our basis b1 through bn, a basis for a vector space V. Then the coordinates of x relative to the basis b are exactly those weights, these coefficients, c1, c2 up to cn, such that x is a linear combination. That makes x a linear combination of our basis vector. And our notation looks like this. The coordinate of x with respect to our basis b is equal to c1, c2 up to cn. And we talked about the graphical representation of coordinates, and what that is if you have a basis, for example, 1, 0 and 1, 2, then these two vectors become your axes, the start of your axes for your new coordinate system. And then these coefficients are how you scale each of these vectors, and then to find your point, you would then use the, if you're in two space, you would use the polygon rule. Otherwise, you would use the normal vector addition rules. So when we have these coordinates in Rn, and we have these coordinate mapping, we could have a coordinate mapping. So in other words, we have coordinates then in our new basis, we have coordinates with respect to our standard basis, and even coordinates with respect to other bases. And what we have is a change of, well, actually that we're going to do in another video. So we're going to go from our new bases back to the standard bases with this change of coordinate matrix, and that's going to be b1, b2 up to bn. And that tells you how to convert coordinates from your b basis to the standard basis. The inverse then allows you to transform x in standard bases to a new basis b. And with this transformation, we have this theorem that says this mapping is both a one-to-one and onto linear transformation from V to Rn. And with the one-to-one and onto, what we have is something called an isomorphism, which means that the notation and terminology for the two vector spaces may be different, but the two spaces are essentially equivalent. So every vector space calculation in V can accurately be reproduced in Rn. And we did that with these polynomials here. And a couple of other examples. And so I do want to say this last idea of an isomorphism is really powerful because it means, one, we talked about vector spaces and how they were abstract, and there's actually many, many things that can be represented with a vector space. And now we can say all of those vector spaces are equivalent, essentially equivalent to Rn. So that's why we spend so much time on Rn, is because once you know Rn, you know how to deal with other vector spaces. So that's it for this video. Thank you for watching.